This conference will now be recorded.
So, very good evening, Deepa. Today, we'll be discussing about nuclear energy and nuclear fission and fusion reaction. See, we had already learned the radioactive decay, and we had seen that during alpha decay, there is a release of energy. Okay, even there is release of energy from a radioactive nuclei in terms of gamma ray also, or gamma electromagnetic radiation. So those things we have already studied. Now, there are two important reactions. These are obviously nuclear fission and fusion, which are very much important in our modern life. Like one among them is nuclear fission, which is actually very important nowadays for power generation. Okay, power generation. There are nuclear power plants. Okay, so in the nuclear power plant, this nuclear fission reaction happens, and nuclear fusion. This is also very important nuclear reaction, which occurs inside sun and other stars. That's why the whole creation is still alive. Okay, so fusion reaction inside the sun is so important, and that is the source of energy, or that is the cause of energy release by the sun. So nuclear fission and nuclear fusion, they have a direct and very important role in our day-to-day life. All right, so knowing this, we need to know that what happens, or what is the reason why during nuclear reaction, like nuclear fission or fusion, why energy release happens, why enormous amount of energy, okay, why is energy released in fusion and fission reaction and fission reaction? So this is the first question we should have in our mind. Okay, what is the origin of this energy? We have somewhat discussed in alpha decay that there is something called binding energy. There is something called binding energy. Before I show you this curve, let me tell you that the source of binding energy, or the cause of this release in energy during fission and fusion, is only because of nuclear binding energy. Nuclear binding energy. This we have already discussed. What is binding energy? Let me write in short B dot E, binding energy. See, this binding energy we had already discussed. Suppose you have constituent, see, by nucleus has proton and neutron. If you have constituent protons and neutrons, and then so these are constituent constituent of nucleus. of a certain nucleus, and then they combine to form a compact nucleus like this. So this will be actually accompanied by some energy, accompanied by accompanied by release in some energy. So why does it happen? We can define binding energy in two ways. One, let us see. In this example, I have taken these are constituent free constituent constituents like neutron and protons of protons. So when they are made or forced to make a compact nucleus, then they are actually bound together in a very tiny space. So they were free. Suppose they were free in the beginning. Now somehow they are made to be compact and they attract each other in a very tiny space. So for binding all of them together in a very tiny space in a compact way, you need some energy. You need some energy, right? That is called binding energy. And in this process, there will be a release in energy. The amount of release in energy is actually the measure of binding energy of that nucleus. Okay, so binding energy can be defined the amount of energy, the minimum energy required to break a nucleus into its constituent, a nucleus into its constituent, right? So this is the energy. So therefore you can understand that you need to supply some energy to break them into if you just want to see the reverse reaction, you have to apply certain energy. So this energy is called actually binding energy. And how it appears? That binding energy can, so the origin of the binding energy is, see, it can be explained according to Einstein's mass energy equivalence. Einstein's mass energy equivalence, mass energy equivalence. Okay, what is that? If there is a disappearance of some amount of energy, suppose delta m, that gets converted to equivalent amount of energy, and that can be written as E is equal to delta m into c square. Okay, during in his special theory of relativity, he has stated that. So if some energy is getting disappeared, then sorry, some mass is getting disappeared, so that mass actually gets converted into certain amount of energy, and that amount of energy you will get by using this delta m into c square. Okay, so this is called mass defect delta m. Now you look here, why this energy release happens, or how this binding energy actually is arising when constituents are making a compact nucleus. Okay, I'll tell you here. Okay, let me tell you here. See, you have neutron, proton. You know the masses of all three, neutron and proton. So if you take the summation over all of them, and if you just see the mass of this nucleus, compact nucleus, it is seen that the mass of the nucleus is less than the mass of the sum over all that constituents. Okay, that's how you get delta m is equal to summation of small m minus capital M. Okay, so this is called mass defect. Mass defect. So what does this mean? Why I am writing this here again? I just wanted you to recap the concept how binding energy is getting, like binding energy is arising. Binding energy is arising because of this mass defect. If you take the constituent elements and their free masses, add them up, and then take the mass of the nucleus, that is capital M. So you look that the mass of the capital M, then mass of the nucleus will be less than the mass of the free constituent elements. That means there is some loss of mass, and that actually gets converted to binding energy, and that energy actually is binding all the neutron and proton together in a compact space. Okay, so you look when here actually there is no binding energy, nothing. So when there is a greater binding energy in any reaction, suppose, so that is for like simple case. Suppose I have two nucleus now. I have two nucleus A and B, two nuclei A and B. If they combine together and make a single one C, then you have to understand whether there will be energy release or energy absorption. In any reaction, you might have seen in chemical reaction also that there is endothermic and exothermic reactions. Exothermic whose releases energy, endothermic whose absorbs energy. In nuclear fission and fusion reaction can also happen like that. So in this case, suppose there are two nuclei A and B combined C. If suppose binding energy of the product, this is the daughter, if the binding energy of daughter, Be of daughter nucleus is greater than the parent nuclei, parent nuclei, then there will be release of energy, release of energy, release of energy. When there is greater stability or greater binding energy, then there will be release of energy. Just make this point clear again. If you have two nuclei, they combine together to make a bigger nucleus C. If the binding energy of the daughter, this is called daughter, after the reaction, what you get, or the product nuclei. If the product nuclei has greater binding energy, then there will be release in energy. If reverse happens, if suppose there is a bigger nucleus, but this is not stable nucleus, when it breaks into two almost similar nucleus, and suppose here Be of the parent P and here Be, binding energy, of the daughter nucleus, daughter nuclei. Okay, so binding energy of daughter nuclei, if this is more than the parent. Okay, if this is more than the parent, then there will be release of energy. What does it mean? What does it mean? If you have a bigger nucleus, you break into separate and two small, almost comparable nucleus, and if the binding energy or the stability of these two daughter nuclei is greater than the stability of the parent nucleus, then there will be release in energy. Okay, I'll give you certain examples. Then now you have to understand how binding energy is varying for nucleus to nucleus. Suppose I take a deuterium. Okay, deuterium, it has binding energy 2.2 MeV. Now you take oxygen, it has binding energy nearly 127.26, sorry, only 6 MeV. Okay, and at the same time, if you take a little bigger again, bismuth, bismuth has 209 mass and 83 atomic number, and see these will have this much binding energy. So binding energy actually increases when your number of nucleons also increases. Look here, nucleons means number of proton and neutron. Number of proton and neutron, that is mass number also. That is mass number Np plus Nn. Okay, or N plus P. I'll write N plus P, that is very simple. A, mass number is A, N and P. So when the mass number increases, that means number of nucleons also increases. And at the same time, you look, binding energy also increases. That means if you require a deuteron to break into two protium, one like one H1 plus you have here nitrogen, obviously nitrogen, like that. If it is happening like this, so you look for the smallest or the lightest element. It has very, see, two A is 2 for this, here A is 16 for, and for this it is 209. So when the number of nucleons increases, then obviously binding energy increases. That means as you have the bigger nucleus, it has greater binding energy. When you have bigger nucleus, then you have greater binding energy. Then see how to compare which one is. See, if the binding energy more, then the stability of that particular nucleus will be more. Suppose in this case deuterium, it has less binding energy, it is less stable than this one and this one. Okay, so greater the binding energy, greater is the stability. But still, this stability can be compared by a term called binding energy per nucleon. Binding energy per nucleon, or binding energy per nucleon. Binding energy per nucleon is the parameter which gives us comparative idea between various elements, which will give rise to release in energy and which will give rise to, like, in other words, which one gives. Okay, let us see the curve itself. So this is the binding energy per nucleon curve we had discussed already. I'll just recap a little bit. See, this is the x-axis, sorry, y-axis. Binding energy per nucleon means binding energy divided by mass number. Okay, in the this curve, you look, if I write only binding energy, then there is a huge gap between this and this and this. Okay, there is a huge gap. But if I write binding energy per nucleon, so this will be around 7.9, and this will be around 8. So these two are now comparable. You look, binding energy per nucleon actually is comparable for both oxygen and bismuth. Binding energy per nucleon can be comparable, but only absolute binding energy may be more in bismuth. So this is one thing, that binding energy per nucleon curve is so important that it gives the idea of nuclear energy through which, sorry, nuclear reaction through which energy can be released, or in other words, it gives the idea of binding energy per nucleon. This curve gives the idea of nuclear fission and fusion reaction. So how this gives the idea of nuclear fission and fusion reaction? Look here, I'll discuss. In this curve, you can see that binding energy increases as the mass number increases. See, from here it is increasing, so deuterium to tritium, then lithium, like that it increases, and it becomes maximum when the mass number becomes almost 56. Okay, for the iron, it is for the iron. So so 56, here it becomes maximum almost 8.5 MeV. Okay, and when there is a maximum binding energy, that means this iron will be most stable element in the periodic table. Now beyond this you look, and below this you look. Beyond this, if you go, energy, binding energy actually getting, like, becoming little bit lesser, and almost it is almost, like, according to the description of this curve, almost up to this 170, almost up to 170 it will be actually. See, it is said that 30 to 170, in this range, binding energy per nucleon almost constant, and that value is actually nearly equal to 8.5. Okay, I think this is 8.8 or something. Okay, for the iron alone. So the binding energy is almost constant in between this range, and when you go too extreme, that means the binding energy below 30 and binding energy greater than 170, these are obviously MeV, binding energy per nucleon, MeV. Okay, then this region and this region, mostly this region and this region, nucleus, actually you can see the nuclei, they have less binding energy than the average value, 8.5, or it is below 8 at least. You can see both side it has less binding energy, around 7 point, like below 7. You can see here, up to here. Uranium, it has around 7.6 MeV. Okay, and in this way, in this region, it has binding energy even less. So if the nuclei are having lesser binding energy, then they are less stable. Less stable. Less stable means they can disintegrate. That they can be broken or tear up into its constituent elements easily. Okay. So now we have to see what happens if we break a bigger nucleus like uranium. Okay, if we break a bigger nucleus like this, I break into two nearly equal mass. Look, in this way, see, uranium breaks into two. That means mass number is getting reduced, and they are going which direction? The greater binding energy direction, right? That means these are more stable than this, the parent. This is uranium, and suppose you have some bismuth and krypton or whatever. Okay, so these two have actually greater binding energy than the uranium. That means they attain greater stability. If greater stability or greater binding energy, then energy release happens. Energy release happens. Okay, in the reaction. So if I break a bigger nucleus into two smaller, almost equal mass of nuclei, and their binding energy becomes greater than the parent uranium or the bigger one, then there will be release in energy. So such kind of reaction is called fusion reaction. Fusion reaction says that if you have a bigger nucleus, when the bigger nucleus is broken into two smaller nucleus, and they have greater binding energy, then there will be release in energy. Okay, we'll see that. So this is called fission reaction, when a bigger nucleus is splitted into two almost equal smaller nucleus, then the binding energy becomes greater, and they becomes more stable than the parent, and in this reaction energy release occurs. There will be a huge amount of energy released. So this is called fission reaction. Now if we do the reverse, suppose in this region itself, if suppose I break a bigger nucleus, if we take some other nucleus also break into two smaller, then also will be releasing energy. But see, if I do one thing, if I take a smaller nucleus and then we combine them to make a bigger nucleus, then what happens? See, binding energy of these two smaller nuclei, they have, suppose this is A and B, and this is bigger one C, they have greater binding energy than this C. So in this case, this is less stable. So there will be no release in energy, rather you have to supply energy. Okay, supply energy has to be done. So this is actually not possible So this is called fusion reaction, when two smaller nuclei are fused to make a bigger one. In that case, there will be either energy is released, or energy can be absorbed. So this binding energy per nucleon curve will help you to understand which nuclei has to be fused to get a bigger nuclei to get energy released. So in this case, look, if I take smaller nuclei and fuse just beyond, say beyond this Fe, if you take two nuclei and then fuse them to get a bigger one, okay, then in this case actually you will not get released in energy, but you have to supply energy to happen to uh, to the reaction to happen. So that means this region is not suitable for fusion, not for fusion, not suitable for fusion. Now go to the lower binding energy region, that means below this A less than 30 even. In this region, if you take two nuclei, light nuclei, and then fuse them to make a bigger nuclei, see the binding energy getting increased here. So the stability increases, that means energy release will happen. So what does this mean? This means that the nuclei which are fused to get a bigger nucleus has to be chosen. Ha, have to be chosen from the elements A less than 30. So in this range below 30, in this place you can actually have fusion reaction, and then you will have enormous energy, amount enormous of enormous amount of energy will be releasing. But if you do fusion here, then you have to supply energy to fusion reaction to happen. But we need to get release, like energy gets released. That is what is our idea. So nuclear fission and fusion, we have understood now that how binding energy per nucleon curve is helping you to understand which region is suitable for nuclear fission and which region is suitable for nuclear fusion. Okay, so higher binding energy, that means if the higher mass number, if your mass number is greater than 170, then you have to break the nucleus into its like two daughter nucleus, so that you get energy released in that reaction. So fission happens in the region here, and fusion happens in the lower binding energy per nucleon region. Okay, all right. So or lower mass number than 30. So we have understood this, like what is like fission somewhat and what is fusion, and in the in the periodic table for which elements you should like you should like which elements you should choose to fuse them to get energy released, and if you understand which elements are suitable for fission reaction. All right, so we have got this idea. Now we will just move on to discuss what is nuclear fission and what is nuclear fusion. I have already told little bit about nuclear fission. So what happens in the nuclear fission? Suppose you have a bigger nucleus. So this is bombarded by high energy neutron. Okay, high energy neutron. Then this becomes, actually suppose this is one nucleus. So this become actually radioactive. This become unstable then. Okay, then it will actually be split into two. So what happens thermally, if you have a nucleus, suppose uranium 235, if you bombard with a high energy neutron, then it becomes 236. Uranium 236 is not a stable nucleus. Then it gets splitted into two. One is barium. Okay, barium, and another one is krypton. Barium has 144 and 83. Okay, let me write it in bigger font. So in this reaction, look, if when this barium and kryptons are released, this barium and krypton, they have actually greater stability. Greater stability. This is okay. Krypton is 89 and 36. 36, and along with that there will be 3 neutron again released. 3 neutrons will be released. 3, 0 and 1. Okay. So generally in fission reaction, a bigger nucleus is broken into or split into two almost equal mass number, like two nuclei having almost equal mass number. Okay, or comparable mass number, and along with that there will be 3 neutron released in that process again. Okay, so this is one example, specific example. I'll write the example in terms of reaction. See, suppose you have thermal neutron, like a very high energy neutron, it bombards uranium 235 92. See, uranium has actually, if you just go back to the binding energy curve, uranium has the binding energy uh, almost 7.6. It is very less, so it is less stable nucleus. Now if you bombard that with high energy neutron, then it actually becomes radioactive. Okay, it becomes radioactive to 36 92, and then it actually gets splitted into two almost equal. Okay, I'm sorry, I'll just write in terms of reaction equations. So barium 56, plus krypton. This is 36 and this will be 89, and there will be 3 neutrons getting released, and along with that there will be enormous amount of energy released. Okay, enormous amount of energy released. So now these neutrons, which are, if I just draw the diagram for this, suppose this is a neutron, it is bombarding the uranium, it is neutron, uranium 235, then it becomes 236, which is unstable. Like that it breaks into two. This is barium and this is krypton, and along with that there will be 3 neutron produced again. So these 3 neutrons again, they will do, they will actually individually bombard another nucleus of this uranium. Okay, and similar things repeats here. Okay, similar thing repeats means each will again produce 3 neutron along with reaction product. Okay, and see, each of them will do like that. Okay, they will produce some product along with that neutron, 3 neutron, some product. So this neutron again will hit another uranium, then they also produce something like that, and 3 neutron. Okay, and this guy also will create another set of 3 neutron. Okay, so this is how, again, see, there will be product also here, and these neutrons again they can take part in the reaction, and this is how chain reaction happens. And at a time, at a fraction of time, maybe there will be a millions of nucleus is getting bombarded by such neutron, and they are getting splitted into two almost equal nuclei, and along with that there will be release of 3 energetic neutron, and each of them will create another 3 neutron along with the product nucleus. Okay, so this chain reaction will actually release a huge amount of energy. So this place is actually called chain. So chain reaction happens here. Chain reaction. So in the nuclear reactor, actually, that is controlled fusion reaction is happening in nuclear reactor, where the the energy is being used to produce steam, and that steam will run the turbine to generate power. Okay, so in the nuclear power plant, where this energy like electricity is being produced, so there actually the nuclear fusion is happening in controlled manner. That means, see, all the neutrons, if they are again bombarding some new nucleus, then it will become a huge like chain. But what generally being done by the use of moderator like heavy water or some other things, other processes there to make this high energetic neutron slowed down such that they will release the energy to the surroundings rather than creating another reaction. So this is what is controlled fission reaction. Generally, if we can control these chain reactions, then we can get the energy for like energy which is released by the neutron in the surrounding, which will increase the temperature of the water in the reactor, okay, and make the steam, and that steam will actually run the turbine. So some of the neutrons are actually absorbed in controlled fission reaction, but in uncontrolled fission reaction, all the neutrons, each and every places, suppose you have one neutron here, then it becomes 3, then it becomes 3, then it becomes 27, then it will be becoming 81. So number of neutron, sorry, yeah, number of neutron increases in every step, and this is how chain reaction happens. And this happens actually during the explosion of a bomb, nuclear bomb. Chain reaction, uncontrolled chain reaction happens, and due to which enormous amount of energy gets released. Okay, so there are many other pathway of this reaction, like say uranium 235 itself. If you see, there are another reaction, like it will create antimony and niobium. It gets into, like, gets splitted into antimony and niobium. 4499, and along with that there will be energy release. And another reaction route is U235 N01. It gives to xenon 140 54, and another one is strontium 94 38, and along with that there will be 2 neutron gets released. Okay, so these are the few examples of fission reaction. And look here, in this case there will be energy released in the mega volt order. So that's why in case of natural coal thermal plant, actually natural chemical reaction happens, and in that case we get energy some few hundreds of kilovolt. But by having nuclear fission reaction, even from a very small amount of uranium, it can produce enormous amount of energy. Okay, so this is about fission. Now I'll just introduce the fusion reaction. Okay, so in this case, one thing is that the amount of energy which is released, that is called Q value. That Q value actually will be manifested in the kinetic energy of daughter nucleus and neutron. Q value will be actually shared by daughter nucleus and neutron, and their that energy will be manifested in them as kinetic energy. Okay, so let us go to nuclear fusion. Fusion, what happens as we have discussed already. In fusion, if you have two light nuclei and then fuse them to get a bigger nuclei, fuse them to get a bigger nucleus, then what happens? Bigger nucleus means A is more. Okay, so in this case, when two nuclei are fused to get a bigger nucleus, it will be having greater binding energy. Okay, greater binding energy. Then whenever in any reaction there is greater binding energy in the product, then there will be release in the energy Q. So this is about fusion reaction, and see, this fusion reaction in general happens in inside the star and sun, because in this case you look, nucleus means always positive charge, so there are two nuclei of positive charge. If they are fused together to form a bigger nucleus, then what happens? Both are positive, they will repel each other, they will repel each other strongly. Okay, so this repulsion you need to overcome to make them fused. Okay, first of all you have to give such a kinetic energy to this nucleus which are going to be fused and create a new nucleus or bigger nucleus. So you have to give or supply enough amount of energy so that the potential barrier, which is potential barrier height, potential barrier height can be can be overcome. Okay, so that much energy is required. That's why you look, if you take two proton, simple example, two proton, and fuse them to get a light nuclei of, if you have two protons and fuse them, then also you need a huge amount of energy to be supplied to them. Okay, just so yeah, so in this case what happens, you need high temperature. How much high it is? As high as 10 to the power 9 Kelvin temperature you need to, temperature is needed for see, to fuse two protons. Okay, to fuse two protons. Okay, and see, this much energy can be there. Even sun has 1.7, sorry, 1.5 into 10 to the power 7 Kelvin. Sun has temperature. So TS, sun has temperature something like this. Okay, so the pressure and temperature, both high pressure and high temperature is needed for fusion reaction to happen. Otherwise, what happens? The repulsion between them cannot be overcome. Okay, so to overcome the barrier height, you need to supply kinetic energy to these two nuclei, so that they can overcome the barrier height and fuse together to form a bigger nucleus. Okay, so that's why you need high temperature and high pressure. And this suitable condition is achieved inside the star and sun itself. Sun and star only. So that's why in any laboratory fusion reaction cannot be done safely. Rather, this nuclear fusion reactions happens inside the stars and sun. And in case of sun, there are hydrogen atoms which are actually getting fused to produce deuteron, and the deuterons, they produce helium. Okay, so there is a mutual production of hydrogen and helium, which is actually, this helium is actually acting as fuel for fusion reaction. Okay, so fusion reaction has few greater detail concept. So there are two cycles of happening, that one is proton proton cycle, another one carbon neutron cycle. So that we'll see in the next class. So in the next class we'll discuss about nuclear reactor and nuclear fusion reaction. So I'll stop it here for today. So Deepa, if you have any question, you can ask me here. Okay, if you don't have any question further, then I'll stop it here. We'll discuss nuclear reactor and fusion reaction in detail in the next class. Okay, so bye for today.